Okay, here we go with classwork 16, Z-scores and T-scores. Today's schedule, we'll start by talking about Oliver Smoot and a Smoot activity to help introduce the idea of what is a Z-score and what is a T-score. Then we'll move on to how we can actually use sampling distribution of means that have a normal shape in a statistical problem. So we'll look at figuring out the likelihood of an individual basketball player having at least a certain height versus a whole team of basketball players having an average height of the same height. Okay, so we'll get to that. So that's today's plan. So let's start by talking about Oliver Smoot and our Smoot activity to try to identify what is a Z-score and what is a T-score. Now, this is a weird story, but it's a true story. Now, Oliver Smoot was a student at MIT in the 1950s. He was in a fraternity and apparently was involved in a sort of prank where his fraternity brothers measured a bridge in Smoots. So they identified how tall or how long one Smoot is, and one Oliver Smoot was equal to 5'7" in height. So that is how long one Smoot is, 5 feet 7 inches, or 1.7 meters. Now, like I said, this is a true story. So we can see if you go to Google and type in Smoot, you can find out more about this, I don't know, odd story. You also see pictures of Oliver Smoot himself while they're measuring the bridge during this prank. And here you can see how they measured him by having him lay down, and they marked where his feet were and where his head was. Had him get up, put his feet where his head was, and they kept counting to determine how many smoots long that bridge was. So imagine this. We have a guy, Oliver Smoot, and he is 5 feet 7 inches tall, or 1.7 meters tall. So you can think about this as sort of a new way of measuring, right? We have this new way of measuring where it's 5 feet 7 inches long. That's how tall this Oliver Smoot was. So if we measured a bridge that was 80 meters long, so we're going to go with the meters here, how many smoots would that be? So I want you to imagine I'm not the world's greatest artist, but let's say we've got some sort of bridge here. All right, so if we know that one smoot is 1.7 meters, and this whole bridge is 80 meters. So I want you to sort of imagine how many smoots would fit on this bridge is what we're trying to figure out. Right? So we could have, like, I want you to imagine one little smoot, and then he gets up and moves and puts his feet where his head was. You can see, just imagine getting up and measuring and marking it over and over and over. We want to know how many of these little smoots are going to fit on this bridge. This is not drawn to scale, so don't just count how many that is. So to figure this out, we want to think about how many smoots can be squished into this amount of space, right? So we take this entire length and we say, okay, if I've got this is one smoot, and here's a second smoot, how many smoots will I get in my 80 meters? So to figure this out, we would take the length of the bridge, 80 meters, and we want to divide by how big one smoot is, which is 1.7 meters. So I'm saying if I have a bridge that is 80 meters long and one smoot is equal to 1.7 meters, right? This is really what we're doing. Then we can figure out 80 divided by 1.7, and we get 47.06. So this bridge is 47.06 smoots long. Okay, so you can imagine basically we can fit 47 smoots head to toe across that 80-meter bridge. Okay, so hopefully everyone followed that okay, right? Since this smoot is more than 1 meter, we see our number has actually gotten smaller. So before we were talking about 80 meters, but now we're saying this bridge is actually only about 47 smoots. So this is a smaller number than we started with. Do you think that means the bridge has gotten shorter? Has the bridge changed? It's gone from 80 to 47. Is the bridge a different size now? Think that through and jot down your answers and then come back and check the solution guide. Now, let's say we have a new bridge. This is a tiny Lego bridge. So this is a tiny little Lego bridge, which is actually only 0.5 meters long, so 0.5 meters. So how many smoots would that be? Maybe pause here and see if you can figure out, okay, if this is how we converted from meters to smoots up above, can you figure out how many smoots will fit on this bridge? So keep in mind, our smoot is how big so this is half of a meter, but our smoot is actually, he's more than 1 meter. He's more than 1.5 meters. He's actually 1.7 meters, right? So this would be one smoot across this whole space, 1.7 meters versus just 0.5 meters. So how many smoots would fit on there? It's actually only going to be probably up to about his knees or so. So again, we can take the length of the bridge. Oops, sorry, that's not the length of the bridge. This is a short bridge. The bridge is 0.5 meters. We can say, okay, I want to divide that into how many smoots it is. So again, we're taking 0.5 meters and saying divide that into smoots, please. I want to know how many smoots that is. And we get, oops, okay. So 0.5 divided by 1.7, and we get about a little under a third, so 0.29. That's how many smoots, or that's what fraction of one smoot would fit on this bridge, right? So not even a whole smoot. So what if we didn't know how tall Oliver Smoot was? How could we convert, or what's this process that we're using to convert from meters to smoots? So you may have noticed in the two examples, what we're really doing is we're taking the length of the bridge, which is originally in meters, and I'm saying I don't want to know how many meters it is. I want to know how long is that in terms of how many smoots could fit in that space, right? So we want these to match so that we can convert to this new unit of measurement. Okay, so whatever the length of the bridge is, we put that on top and then divide by how long is one smoot. In this case, we know one smoot is 1.7, but that would be however tall smoot is. Let's say that smoot was actually 6 feet tall, or he was 6'6", whatever that value is for how tall one smoot is, that's what we would plug in on the bottom to convert from one unit to our new unit of measurement. Okay, so to review, what is a smoot again? And what are we using it for? So a smoot, in this case, is the height of the student, and that would be good old Oliver Smoot. And then what are we using it for? So we're taking this original unit, Oliver Smoot is a certain height, and we're now using that height or that length or that distance to measure the bridge, right? So we're using it as a unit of measurement. And in this example, it would be 4 bridges. So go ahead and pause and reflect on that. Well, hopefully you recall that a standard deviation is really the average distance from the mean. So we've talked about it in the past as a measure of spread, but now we're going to use it as a measurement or a unit of measurement for distances. So just as we could say, okay, this length, this length is equivalent to 1 smoot? Well, instead of having a smoot, we're going to say, okay, well, the standard deviation in this case, how much do we see that variation? Well, for this particular one, there's this much variation on average. We see the standard deviation is 6, or it's 3, or it's 10, or it's whatever it is, right? We take how long is one of those standard deviations, and now this is going to be our new measuring stick or our new measuring tool. So imagine you have like a measuring tape or a yardstick that is set to magically be equal to 1 standard deviation for any of those distributions that you're looking at, any of those samples that you have. Okay, so instead of 1 smoot and saying how long is this in terms of smoots, we're going to say this is how long 1 standard deviation is. How many standard deviations will fit in this particular distance that we're talking about? Okay, so this sounds confusing and vague for now, but we are going to use this to connect to z-scores. Okay, so let's take a look at the definition of a z-score. So a z-score is a number that indicates how many standard deviations a data point is from the mean. So if you imagine, if we have some data set, let's say we're just going to go with a little normal curve here, and we identify where the mean is. So remember we were saying, oh, we can indicate the standard deviation is, so much, or is a certain value that represents the average spread around the mean. So we could say, okay, well, this is how long 1 standard deviation is. Then if I have a point that's out here, how many of these standard deviations will fit in this distance? If it's really close to the mean, if my point is on the mean, then it's 0 standard deviations away. If it's a little over here, then it's, okay, how many standard deviations fit in that distance? What if my point is way up here? How many standard deviations fit in that distance? How many little smoots could lay down on that bridge and fit in there? So this is how we're going to be using standard deviation. So this number indicates how many standard deviations a data point is from the mean. So that is what a z-score is. The z-score is how many standard deviations fit between a point in your data set and the mean of your data set. So we have to figure out where's the mean, where's the point we're talking about, and then how much distance is there between those two things in terms of how many standard deviations fit there. So we're going to connect that definition to the formula for z-score. So this, what you see right here, is the formula for a z-score. So let's break it down a little bit. The top part says x minus mu. And keep in mind this definition. So x, well, that's just some data point in our data set, right? X could be any data point. What is this mu symbol for? Well, hopefully you remember that that symbol mu represents, or that symbol is representative of the population mean. So think about this. This part of the formula, the top part of our Z-score formula, is saying take some data point and then subtract the mean. So think about, what is this difference between these two? What is that telling us? And think about it in terms of the Z-score definition that we have. And then consider the bottom of this Z-score. Why are we taking this difference between a data point and the mean, right? We're finding a distance between some point and the mean. Why do we then divide it by standard deviation? What does that do for this part of the formula too? Right? So think about our smoots. Think about what this top part of the formula represents. And then think about, why would we divide by one standard deviation? Will help to remember, what did we do here? Right? So hopefully that will help you start to connect some of these ideas. And then once you've had a chance to think these through and jot your notes down, you can come back and check out the formula, the solution guide, and I can explain more. Now, we haven't seen this video yet, but we're also going to be talking about what are called T-scores. It's very confusing. We have Z-scores and T-scores, and they look very, very, very similar. If you look at this formula for a Z-score and this formula for a T-score, what's the difference? And then what do you think is the definition of a T-score based on how similar these formulas are? Then think about, what is different? What is conceptually different? What's the difference between this symbol and this symbol? What's different about those two formulas? And think about conceptually what they represent. Finally, here's another formula for T-scores, because as if it wasn't confusing enough, we have Z-scores, and there's actually two different formulas for that. We'll come to that soon. And T-scores, and there's two different formulas for that. So it depends on the situation which one is being applied, but they're all extremely similar. So here's our other version of a T-score. So here's one T-score, and here's another T-score. This SE at the bottom, that's our standard error. And we have the formula for it here too. So again, do your best right here. This is a T-score. What is the definition? What's different about this T versus this T? And what does that tell us? What is the difference in terms of the concept? This one's going to be a lot harder. If you struggle with this one, don't worry. We're going to be revisiting this material lots and lots of times, but I'm just trying to get you to stretch that a little bit right now. And then what is similar about those formulas? Why are they both called a T-score, do you think? And I'll give more info on this. So, what is the difference between the definition of a standard deviation, what it is, and using it to find a T-score or a Z-score? So we have our little analogy. How are T-scores and Z-scores like Smoots? So as we said, a standard deviation is the average distance from the mean. Then think about a smoot is how tall or long, I guess you can consider, Oliver Smoot is. Okay, so that's the what is it? What is a standard deviation? What is a smoot? And then how are we using them? So with the smoots, we talked about using those as a unit of measurement. Right? How many smoots will fit on that bridge? With our standard deviations, we're also going to be using it as now a unit of measurement. So we identify, okay, how long is one standard deviation? And then how many of those are going to fit between whatever point I'm interested in and the mean of that sample. So we're saying, okay, there's a certain distance between the mean and the data point, right? We're saying now, not only how big is this distance, but how big is it in terms of how many standard deviations will fit in that distance? Is it one standard deviation? Is it two? Is it three? Is it half of one? Right? We want to know how many standard deviations fit in that space, just like we wanted to know how many smoots will fit on the bridge. Okay, so keep that in mind. So our t-scores are going to tell us a distance in terms of how many standard deviations fit in that distance. Okay. We're going to measure distance in units of standard deviations. That's what I just said. Instead of in the raw units. So instead of saying, like when we talked about St. Louis and San Francisco, and we talked about how many degrees different or how many degrees something was. Or maybe talking about inches, like how tall someone is, or percent correct on a test. Whatever thing we're talking about, instead of talking about it just in terms of the raw units, how many points, how many percent, how many inches, how many degrees, we want to know, okay, not really how many inches, but how many standard deviations is it? Okay. So our t-scores and our z-scores, which are again very similar, and there's going to be another video that really kind of illustrates how they're different. These both help us to understand how far something is relative to how spread out the data for the population is, right? So imagine if we had one sample that's like this and one sample that's like this, right? So if we have, here's this mean and here's this mean, and the standard deviation is this long here, but it's this long here because it's a really big standard deviation. So if we have a point that's out here, we're going to want to figure out how many of those standard deviations fit in that space. If we have a point that's could be anywhere, it could be here, it could be here, it could be here, but let's say our point is here, we want to see, okay, if my standard deviation is this big, how many standard deviations fit in this bridge or in this space, this distance between
my data point, and the mean. So the SDOM, or the sampling distribution of means, is typically normally shaped. So not like one of these really flat or really skinny curves, but generally a nice normal shape for our SDOMs. What is an SDOM again? That is the sampling distribution of means. So that means if we take a sample and we calculate the mean, then we're going to go plot that mean. Then take another sample and calculate the mean and add that to wherever it falls on here. Take another sample, calculate the mean. Maybe this one's way over here. Right? So we're stacking up all these sample means until we get this nice curve, just like we saw in those online demonstration simulation activities. Sorry, I'm missing the vocabulary right now. Okay, so we've got our SDOM, we've got our T-scores. So what we're going to do is, since we know this SDOM is basically always normal as long as we have enough people in our sample, we're going to be using that to determine, okay, if this is the SDOM based on the null hypothesis being true, and I've simulated this, and I have just my one sample, because we usually don't do sample because research is expensive and it takes time and money. We usually only have one sample. But when we find that sample and we test and we say, okay, this is the mean that I got, well, this SDOM is made up of a whole bunch of little possible, what are all the possible means that we could have gotten from all these hypothetical samples if the null hypothesis was true? So keep in mind, all these are a bunch of means all piled up. So with our empirical sample, our actual data that we collect, we can then say, okay, well, where does this fit in this curve of all these means that are possible? If this mean, I'm going to color it differently so it stands out. If this mean falls, let's say it falls like right around here, right around the mean based on the null. Well, if it falls here where there's a bunch of them, then that would be not unusual. I mean, that would be, okay, yeah, there's a whole bunch of means just like my mean if the null hypothesis is true. Well, if there's a bunch like mine, if the null hypothesis is true, then I don't have good evidence that the null hypothesis is not true because mine is consistent with what we would expect. Okay, alternative scenario. Ooh, yeah, I was just trying to get rid of the the green. So, alternative scenario, let's say our actual sample mean doesn't fall here in the middle, but it falls way out here. Well, if our mean is way out here, but most of the means we would expect if the null were true are over here, then that means this is super weird. Why is this mean way out here if we would expect, if the null is true, the means to be over here? So when we find cases where these means they're sticking out, they're in these areas where there's not very much happening, then it's weird to see our result out here where there's hardly any sample means. That's odd. because that's unusual. It's unlikely to happen. If we get them here in this middle section, yeah, that's not unusual. That's not weird at all. We would totally expect to get a bunch of these if the null is true. If we get out here, that's when things get interesting. Okay, so we're going to end up taking this idea of the SDOM. We have our empirical sample that we calculate our statistics on. We calculate the mean, and then we say, okay, where does this mean fit in among all these possible means that I could have gotten if the null hypothesis were true? If it's somewhere in the middle, I'll think that's not that weird. I guess the null hypothesis might be true. If I get one way out here where there's almost nothing, then I'm going to go, whoa, that's really weird. Why? What is it doing out there where where it's like the middle of the desert and nobody's out there? That's weird. That's unusual. I think maybe the null hypothesis is not actually true because it would be so weird for my result to be way out here. That means this seems unlikely to be true. Okay, so this is the first of many introductions to this idea of hypothesis testing using sampling distributions. We are going to revisit this a lot. We are going to keep going with z-scores and t-scores. So next we'll see, okay, this is all a lot of nice theory, but show me what can I really, really do with this? Show me how to do a problem, right? So that's what's coming up next. And I will see y'all soon.